This is example problems for homework 3. First example problem is problem 15.22 from the textbook. This is very similar to 15.21. 15.22 wants us to do a pseudo NMOS of y equals AB naught plus A naught B. This is an XNOR. And so because we want to do a pseudo NMOS, we want to look at it in terms of y naught. So we're going to go through, we're going to transform this into y naught. So we're going to take the naught of both sides. Then we're going to distribute this naught. Then we're going to distribute it some more. Then we're going to multiply these out, and we're going to come up with A and B, or A naught and B naught. And so the knotted expression of this is A or B and A naught or B naught. And just to confirm that this is true, we can do a quick truth table. So if we have 0, 0 here, this is going to be 0, 1. This is going to be 1, 0. So this is going to be 0. If we have 0, 0 here, this is going to be 0, 0. This is going to be 1, 1. So y naught's going to be 1. And that's what we got. Because this is for y. This is the y truth table. But the opposite of this is y naught. So if we have b equal to 1 and a equal to 0, then we get a y of 1. If we have b equal to 1 and a equal to 0, we have a y naught of 0, which is the opposite of that. A equal to 1, b equal to 0, y of 1, y naught of 0, a equal to 1, b equal to 1, y of 0, y naught of 1. So these two expressions are equivalent. So to do our pseudo NMOS, we're going to have our pull-up network simply be a PMOS connected to ground at the gate. And so all this is doing is acting as a resistor. So when our pull-down network is on, it's pulling it down to 0. When our pull-down network is off, it's V out is just going to VDD. So our pull-down network, we're going to have an A, we're going to have a B, and then we're going to have another branch. And this is going to be A naught, and this is going to be B naught. And that's all there is to it. The part that makes this a pseudo NMOS is this PMOS right here that's just in bias. That's the only difference. It doesn't have a pull-up network, it just has a PMOS in bias. So that's all you want to do. You want to get it in terms of y naught, because that makes doing the pull-down network much easier, because then ORs are just different branches and ANDs are just in series. That's all you gotta remember. The next example problem that we're going to do is 15.27. And so this is going to be an example for 15.28, which is actually the exact opposite problem. For 15.27, we want to look at figure 17 from the book, and let me draw that for you. Figure 17 has something that looks like this. Well, this is VC. And then it has an input. VI. This is time. VI 0, and then it's VDD. And V out. This is time. It's going to have an output that looks like this, where this right here is VDD minus VT, and this point right here is going to be VDD over 2. This is going to be tplh. So we want to find tplh for this figure, and we have given that W over L equals 1.5, VT naught equals 0.4 volts, gamma equals 0.2 volts, 1/2, 2 phi F equals 0.88 volts, VDD equals 1.2 volts, and Kn prime equals 500 microamps per volt squared, as well as C equals 10 femtofarads. So what we're going to want to do is use the average current method. I'm going to find tplh. So the average current method tells us that tplh is equal to C VDD over 2 divided by ID average. So how we're going to find that average is we're going to use this equation. And we're going to find the value at minimum and the value at maximum at VDD. And because our VT is changing, we got to use this equation. Both of these equations are in your book in chapter 15, section 15.4. So all we're going to want to do is we want to find ID at 0. We want to find ID at tplh. So we're going to do ID at 0. Doing 1/2 times 1.5 times 500 times VDD is 1.2 minus, at time t equals 0, V naught equals 0, right? Time t equals 0, V naught equals 0. We got to find our VT here. And our VT here is just equal to VT naught. Because this right here, V naught, is equal to 0, so it's 2 phi f minus 2 phi f, or square root of 2 phi f times 2 phi f. So our VT naught is 0.4 minus 0.4, all that squared. And that gives us 240 microamps. Now for ID at TPLH, our V out equals VDD over 2, as you can see right here. Right here. So here V out equals 0. Here V out is going to equal VDD over 2. So it's going to start off the same way. 1/2 times 1.5 times 500. This is just Kn. Our VDD is still 1.2, but now it's minus 0.6. And we have to find our VT for this new V out. So our VT here, VT at 0.6 is equal to our VT naught, which is 0.4 plus 0.2 times the square root of 0.6 plus 0.88 minus the square root of 0.88. And that gives us 0.46 volts. So minus 0.46 here, all that squared. That gives us 7.35 microamps. So ID average is just equal to the average of those two. 123.7 microamps. Plug that into up here. TPLH equals 10 femtofarads times 0.6 volts over 123.7 microamps. And you get 0.049 nanoseconds. Because femto is 10 to the negative 15th and micro is 10 to the negative 6th. So 10 to the negative 9th, which is nano, which is our final answer. So for 15.28, which is on your homework, you're going to be doing the exact same thing, just in the opposite direction. So it's going to be going from high to low instead of from low to high. So it's going to be very similar. You're just going to change it up slightly.